Next up, we have three propositional variables, P1, P2, and P3. And next, we want to demonstrate that A is there is a what was it? Semantically consequential. So we must show that each of these. Okay, so I'm gonna drop the first one. So P1 implies P2 implies P1. So this symbol here basically acts upon the entire expression. I'm actually gonna just let me write it really big to make it more apparent. So, right, so what does this mean? It means that we have to do the following. We have to prove that for the table of truth of any combination P1, P2, P3, there is a tautology, meaning, as we did before, tautology meaning that they're semantically equivalence, which is true for all the scenarios because the formula is already laid out, and that's step number one. Check if it's a semantic equally semantically equal. Yeah, I got it right the first time. Semantically equal valoration, aka tautology. So that's step number one for the where was it? The semantic consequence. This one right here. Let me actually make it more explicit. And then, actually, that was something else. Right. Maybe a better idea would be to put this here. So, I mean, yeah, it's suboptimal to have it there, I know. However, will I struggle to find space? I will not. Bear with me for just 1 second. I'll maybe cut this part out. Or if I forget, because the life of a student slash worker is very, very hard. So we got a set of formulas, which is the definition of this symbol, and then we can erase all of this, and here we have the semantic consequence, aka equal valoration test. There. Can't make it more explicit than this. I could actually. That's a lie. Whoa, that's trippy. Oh crap, pardon my French. Yeah, this this was confusing me for a while. It's not a semantic consequence. I just checked with my professor. That is actually a typo from the manual. It's just of consequence. So the reality is that phi, in this case, the correct interpretation will be is of consequence. So, and by finalizing the expression, phi is of consequence in value. So in value, or is of in value to the subset of to the set of formulas. Yeah, that's right now. That's correct. Okay. Anyways, I've been using it. I haven't been using this, so no mistakes were made up until now. So we're good. Alright, and okay, so let me rewrite this. So the first step is to check if the result, or if the valoration is let me just to be sure now, because the explanation was correct. It's just that the wording, the phrase had a typo in it. So the correct interpretation is that, yeah, here we go, is that the valoration must be the same for any combination. And by this we mean we have to use the truth table and display all the combinations that we can get for P1, P2, and P3. For this unique example, we only needed the first ones, P1 and P2. P3 isn't involved. And so it's probably more useful to immediately write the full table here. So we have P1, P2, P3, or should I say more organizationally correct. Okay, so it should provide us with 8 results. So we got this one and that one. And I'm assuming that you already know, of course, how these tables are, the truth tables are made. You simply begin in a binary base. So what this means is you get the first value, which is 0, the second value, which is 1, the third value, which is 3, the fourth value, which is excuse my French, this is 2, and so on. And then we get 1, 0, 0. Whoops. Let's give this some structure. 1, 0, 1, 1, 1, 0, and 1, 1, 1. And ta-da! We have a very orthogonal table. So as I was explaining, and here we have a 4, here we have a 5, a 6, and a 7. These are in fact 8 numbers. Then why does it finish in a 7? Because we're lagging behind 1. We start with 0 instead of 1. And okay, so that's a whole concept, which is binary, understanding binary and knowing how to convert it. And here in logic and computation is the step beyond learning. So if you don't know, I will suggest that you search up digital systems and truth tables to see how they work. Yeah, digital systems course or tutorial. So that's that. Right, now here we go. We got A, and the first thing we have to do is check if the valuation is the same for any combination in regards to this problem right here. Okay, and then the second step is that it's quite similar actually. It's checking if the valuation is 1 for any formula, or for any, pardon me, for any combination. So I guess this implicates the second step, so it's weird why they say it like that, but the educational system is not perfect. And that is a truth that we can all agree on. So let's see. The Validation